Hello. So welcome to the day 5 of second week of this lecture series. We have been discussing about the point groups, and we have been trying to find out point groups of different molecules. So as I said at the end of the class yesterday, we will now try little the molecular structures which are little tough, and I have been telling you, and I will again emphasize on that you should try to either use certain models or bring your own model with taking straws and all, which is not too difficult to do, and you will slowly develop an intuition if you practice with those models by looking at certain molecules, whatever complicated structure that may have. You will be able to find out the symmetry operations. Okay, so it depends a lot of on your on the practice. So I request you to you take a lot of molecular structures, try to find out. Okay, and let's get started with one such molecule. So and this probably will be my last molecule that we will be discussing, and rest of the things that you should practice yourself. So we will discuss about a molecule that you can see on your screen is COEN whole 3. Okay, so it's an ethylene diamine complex. So tris ethylene diamine, cobalt 3 plus. You can ignore the charge. Now, what you see here for this molecular structure, that okay, there are 3 ethylene diamine which are bidental ligand and all are similar type of ligands. But from there, if you have to find out the symmetry operations that are present for this molecule, it may be little tough. Okay, so although I have shown here in this particular figure the exact stereochemistry, but it may be still difficult for you, particularly who are the beginners here. Okay, now for such situations it will be advisable that you draw the structure in a a little bit better way, which helps you finding out the symmetry operations. Okay, so instead of drawing in terms of this amine and CH2 again amine, you can think about it as like a ribbon. Okay, so that part is same for all the EN ligands. So you can treat them as just as a ribbon, which is like an arch. You can think of exactly what is shown in this figure. So this blue balls are representing the amine, and the ribbons are the 2 CH2 groups. Okay, so from here, if you draw it in such a way that one of this amine group occupies the equatorial plane, then another 2 amine will be protruding toward above the plane, and another will be below the plane. So axial points will be occupied by other amine groups of 2 other ethylene diamine. Now, if you look at this carefully and try to find out the symmetry symmetry elements first. So what will be the principal axis of rotation here? So think for a moment. You can pause the video for a second, look at it, and try to find out where will be the principal axis of rotation and what is the order of that. So what is the CN? That's my question. So one thing you can easily figure out from this way of drawing here, that an axis which lies on this equatorial plane and dissects this angle, this can act as a C2, because this amine will come here and this will go in its position, right, and this 2 also will interchange their positions. So in a sense you will get an indistinguishable structure. Now this is a C2, right? This is a C2. I do not know whether this is C2, whether this is C2 prime. I am trying to figure it out, correct? So since I can get one C2 by putting this En on equatorial plane, similarly I can redraw it by bringing this ethylene diamine into the equatorial plane. I can get one more C2 and then the third one by putting the third En in the equatorial plane. So I get 3 C2 axes, okay. So I get 3 C2s. Then what are the other symmetry operations that I can think of that will be necessary for me? So I have to think about perpendicular C2s. Now I see that there are 3 C2s, right? So these 3 C2s are they like the 3 C2s in case of say alene, or something different? For that actually you need to draw this structure even better way, okay. So that's why you should always try to innovate the way of representing one structure so that it becomes very helpful for you, and that's what I am now going to show you, okay. So this is nothing but this structure, okay. So this and this are pretty much same. Now I will orient it in such a way that it is helpful for me. So I can reorient this same molecule in this way. So what I am trying to do here, I am trying to play with the perspective, right. So in this particular perspective, so see this is one ethylene diamine, this is another ethylene diamine, this is another ethylene diamine. So now things becomes very easy, right? This looks like just like a propeller. So if I start from this particular point and if I give an 180-degree rotation, it will reach here, and this guy will reach here. So I got a C3. Very well. Now I got this 3 C2s earlier, right? By finding an axis which will go through this equatorial plane, and it will bisect the angle that this 2 amine of one ethylene diamine forms at the cobalt. So that is the C2. So we got 3 such C2s. So if I apply the same technique here, obviously it has to go through the middle of the ethylene diamine, this arc, right. So I can have one axis in this direction. Now think about it, it's like a propeller shape, and the situation is to some extent you should find out the similarity. To some extent the way it has been drawn here, it is to some extent like that ferrocene staggered conformation problem, right. So you try to do it yourself. You can just cut piece of papers and you can fold it accordingly, and then do this rotation. You can just put something like a needle or some very narrow object which will act as your axis, and then you give the rotation and you will see the effect, okay. So here, so this guy, okay, so we were considering this axis, right. So this point which is above the plane of the paper will now go below the plane of the paper, like here, and the point here which is below the plane of the paper will now come up, and same thing will happen for these 2 ends also. So obviously I have the Cn, and that was already verified here. So but here you are confirming that, okay. So you got 2 more C2s here, okay, one along this direction and another along this direction. So you got 3 C2s. Now the way my C3 is above the plane of the screen, correct, and these C2s are on the plane of the screen, correct. What does that mean? That means these C2s, all these C2s are perpendicular to the C3 that we got. So, we are going toward finding out the point groups. So, I got a D type point where the principal axis is C3. Now, do we have any other symmetry elements present here? Do I have a sigma H from these structures? No. Pretty much like this ferrocene at staggered conformation. So, I do not have any sigma H here. Now, do I have any sigma V? So, I do not have any sigma V's here, because this case is also slightly different from the staggered ferrocene conformation. Okay, and that slight difference, is in the the occurrence of sigma D planes here. So, we do not have a sigma plane, because I have this bond here. In case of the staggered ferrocene, I did not have any bond between this top and bottom layer, right. So, here I do not have any sigma D's. So, what is my answer? What is the point group? The point group is D3. One C3 as principal axis of symmetry, 3 C2s perpendicular to it, and no sigma planes. So, my point group is D3. Okay. So, you can try with various other complex molecules, try to find out the point groups. Okay. So, I request you to practice as much as you can. Now, we will quickly go through certain properties of the symmetry operations. So, we talked about the product of symmetry operations. Particularly, we took the example of water molecule, correct, and for them we showed how this 2 sigma, if we operate successively, will result something similar to that one could get with C2 operation. Now, we will try to go through that in a general way real quick. So, this whole this product of symmetry operation, it stems from the very basic principle of or definition of the group itself. So, any two operations which belongs to this group are the elements of group. So, the product of any two operations will be definitely a member of this group. So, therefore, we should be able to find out that what is the resultant of product of two symmetry operations by looking at the the group itself. So, the way we do, we mentioned it earlier also. So, here we are being a bit explicit in this, and suppose I operate a B first. B is an operation belonging to particular group, and then on the resultant we operate A, which is another symmetry operations. Then whatever the effect we get, that can be actually obtained by operating some another symmetry operation C alone. Okay. So, we start from right, then go to the left. Okay. So, we first operate B here and then do the operation A. Fine. So, that is the convention that we will follow. And also here we will again mention that in case it does not matter, because in case of normal groups of numbers and all, we may find like so like we saw 2 into 3 equals to 3 into 2. So, the order, the way I am doing this combination, it does not matter, but in case of this symmetry point groups, in general this is not the case, rather this is a special case. So, when this special case happens, that is AB is equals to BA, okay. So, the order does not matter. In that case, we say that A and B commute, okay, and they have certain implications, okay. And when all the symmetry operations commute with each other in a symmetry point group, we call that as an abelian point group also. And now you remember in the last class we asked you for that point group of H2O2 in cisplanar and transplanar configurations, what speciality about that point group. And if you go back and now check this combinations of any two symmetry operations, you will see the order does not matter, and you will find out that both of these symmetry point groups, both of them have order 4 and both of them are abelian. Okay. So, now we will try to operate symmetry operations on some generalized points. The reason of doing this one, because in a later stage when we will form the particular representations for a group, for any given group, we will be using certain basis functions, and in many cases the basis functions will be nothing but the 3n Cartesian coordinates of the molecule, particularly say if talking about molecules and all the atoms, and that will be very, very vital when we go to something like vibrational spectroscopy. So, here I thought, okay, let's do a practice with a general coordinate, and we will do the same type of thing that we have already looked at, like two operations we will take and then operate successively and then look at the resultants. Now, instead of taking a particular molecule like we have been doing with, like water or ammonia or something like that, instead of that we will take any generalized point on the space. So, what I am saying is, if you concentrate on the board, we will take any point, any given point on this space. Okay. So, let us say this is my Cartesian coordinate system x, y and z, and I take a point somewhere, some point P, whose coordinate is anything, say x1, y1 and z1. Fine. And then we will operate all the symmetry operations on this. Okay. So, we will tell you what exact operations that we will be doing. So, this particular point if I consider, then I can break it in its x and y and z coordinate. Okay. That will help us in many ways. So, this has an x1. So, suppose that x1 is here. Okay. So, this is x1. Then correspondingly I have some y1 here. So, let's take it somewhere here, that will be helpful for us. So, this is my y1, okay, and then this is my z1. Fine. So, this is the x, and this distance is y, and this distance is the z1. Okay, x1, y1 and z1, and we will operate all the symmetry operations on this. So, if we come back to the screen here, so we are considering this general point x1, y1, z1, which we have given a name P. Now, if we apply any operation, so that will send this point P to another point, say P1, which is having coordinates x2, y2 and z2, and if we apply another operation on this one, then the point will go to another configuration x3, y3, z3, right. There is no confusion about that. So, we need to find out how we can go from x1, y1, z1 to x3, y3, z3. So, we went to x3, y3, z3 by operating two symmetry operations on this point. I want to go to x3, y3, z3 by a single operations. Okay. So, that is my motto. So, now suppose I take this point x1, y1, z1 and I operate C2x. So, C2x is as you can see on the board. So, C2x means there will be an C2 axis which is lying along x. Similarly, C2y will be lying along the y axis. So, C2y, C2x, and here I will have C2z when it is following the z axis. So, if I do C2x operation on x1, y1, z1, so what will happen? So, here if you look at, so I am operating C2x, correct. So, this x will not change, right, because x1 is x1 and I am just rotating x axis, nothing is going to happen with x, while this y1 it will now come here becoming minus y1, and same thing will happen to z1, it will become minus z1, and that is what is shown here. Now similarly, if we perform C2y on this one, so you should try out this one, draw it like this and see how the points changes their coordinates upon this symmetry operation. So take this generalized C2s and apply it on this general point x1, y1, z1 and find what happens next. So if you apply C2 on the result, you get minus x1 minus y1 minus z and z1. Okay, so you can apply C2z now on x1, y1, z1. So what will happen if you apply C2z on this particular molecule? Nothing will happen to z, correct? But the xy plane will change their orientation by 180 degree, very easy. So x1 will become minus x1 and y1 will become minus y1. So you get minus x1 minus y1 z1, the same that we got here. So these two are equivalent. So I can find out the product of C2y, C2x, and this is C2z. Now there is one thing interesting here, that this C2x and y and z, they are perpendicular to each other because we are following the Cartesian coordinate system, right? So this relation is generalized relation, so it's valid for anything and everything. So this also tells that if you just find out that there are two C2 axes perpendicular to each other, there must be a third C2 which is perpendicular to both of them. So in other words, if there is C2x, C2y, there must be a C2z. So that is a nice consequence of this. Okay, so similarly we can find out using several other operations on a generalized point. So like here we operate this C2z on this xyz, and here instead of taking arbitrarily x1, y1, z1, we are taking this x and talking about when we get like x minus x1 upon operation of some symmetry operation on this positive x1. Here we will use a notation which is like minus x1 is essentially x bar 1. Okay, so with that notation, if we look at upon C2z operation on this xyz, which is equivalent to x1, y1, z1, we are not writing 1 to 1 subscripts, then we get x bar, y bar, z. And if we operate sigma xy, so sigma xy is a plane which is on this xy plane. Okay, so z is not in the plane of the reflection. So the z will be the only thing which will get reflected. So I get z bar, but xy will not change their positions, correct? So I got this one. Now I have to combine C2 and sigma xy. So upon doing that, ultimately I get this x bar, y bar, z bar. Now think about it. You have x, y, z. You are doing this operation C2 followed by sigma, or sigma followed by C2 actually. Then you are getting x bar, y bar, z bar, which is like complete inversion of the point. You don't have to do anything. You immediately know if some operation completely inverts the any given the coordinates of a given point from x, y, z to minus x, minus y, minus z, or in other words x bar, y bar, z bar, then that operation must be an inversion operation, and that's what exactly is shown here. So ultimately what you get is the C2 sigma if you operate in such a way that C2 is perpendicular to the sigma. Okay, so if you are applying C2x and sigma yz, then it will give you an I or inversion operation. Okay, so there is one more thing that I will quickly go through, that is the equivalent symmetry operations and equivalent atoms. So suppose we have one particular symmetry element. Say you think about the case of ammonia. Let me quickly draw that. So you have Okay. So, this is one hydrogen, one hydrogen, one hydrogen, and then we are drawing the planes like this. Okay. So, these are the planes. So, sigma V1, sigma V, say sigma V prime, sigma V double prime. Okay, these are the three. Now, I have C3. So, now if two elements I have in general, say I have an element first A, which I will call this sigma V. So, sigma V is my A. Now, if sigma V can be transformed into sigma V prime by an operation, which here is clearly C3. So, if I operate C3, this plane actually is coming here. So, sigma V is coming to sigma V prime. Similarly, I can have an operation which can take sigma V prime to sigma V, and that will be C3 inverse. What is C3 inverse? C3 inverse is C3 square. So, this sigma V and sigma V prime, they are called equivalent symmetry operations. Now, this has certain consequences, like all the molecules, all the atoms in a molecule, which can be transformed into each other through a equivalent operations, the way I showed in the same way. Then those atoms will be equivalent atoms. For example, if you take benzene, all the carbon atoms are equivalent. But for example, you take something like a naphthalene. So, in naphthalene, this alpha carbons, beta carbons, and the carbons at the 9th and 10th position, they are not equivalent. What does it mean? That you cannot say, for example, if I quickly draw the structure of naphthalene on this side. Okay. So, suppose I am talking about, say, let's this carbon. Okay, I am not worried about the pi electrons clouds here. So, this one, this one, this one, and this one. This can be converted into this, because I can use a C2, I can come from here to here, but I cannot. So, if I mark these positions by these crosses, I can never transfer this one over here by any symmetry operations belonging to this point group. So, these two are non-equivalent. Okay, and this equivalent atoms in a molecules will have the same chemical properties. On the other hand, non-equivalent atoms will not have the same chemical properties. So, that is very much evident in case of, say, NMR spectroscopy. Okay. So there are a few quick points I will run through here, which will be pretty important to note. That is, the following pairs of operations will always commute. So, what are they? Two rotations about the same axis, they will commute. Reflections through planes which are perpendicular to each other, they will commute. So, like sigma xy and sigma xz, they will commute. Okay. So, the inversion and any reflection or any rotation, they will commute. Two C2 rotations about perpendicular axis, they will commute, and rotation and reflection in a plane perpendicular to the rotation axis, that we just saw. Okay, that C2 and sigma. So, they will commute to each other. So, these are the few symmetry operations that commute. All right. So, now there are two things that I will mention before we end class today. That is, we can relate the symmetries with some physical properties. So, the first thing we will talk about something like optical isomerism. So, optical isomerism arises from chiral structure. Chiral structure means if a molecule has a non-superimposable mirror image, then we can have this optical isomerism. Okay, the molecule is chiral, so we can have optical isomerism. So, a molecule which is non-superimposable on its mirror image is known as a chiral, and that shows optical isomerism. That is, that changes the plane of the polarization when I use plane polarized light. Okay. Now, there are certain point groups which turns out to be chiral in a true sense. Which are they? So, they are C1 means it has no symmetry other than identity. Cn, that is, it has only proper axis of symmetry, nothing else. and Dn, something like that COEN whole 3 that we looked at. So there are other point groups like T, O and I, which are extremely rare point groups though, but the C1, Cn and Dn, they are not rare, they are quite abundant, and we see this effect of chirality from these molecules. Now why does it happen? If you have a mirror plane, that can actually produce a mirror image, okay, and that becomes superimposable. So having a mirror plane in that molecule will make sure that it is not chiral, it will not show any optical isomerism, and same is inversion. So that two are very easy to figure out. Now other than that, if you have Sn, what will happen? In S you rotate and then take a mirror image on the perpendicular plane. That will ensure, you can try it out with any given structure having Sn, that will actually produce a superimposable mirror image. So in order to show, for a molecule to show optical isomerism, it must be devoid of Sn axis. That is a rule of thumb. If some molecule has Sn axis, it cannot show any optical isomerism. There are exceptions, but that is because of something else, that is because of overall structural change, because of complete other reasons, not due to that has nothing to do with Sn axis. So so that is about the chirality, and you can try to remember those point groups that I mentioned, that C1, Cn and Tn, which end up giving a chiral structure and hence optical isomerism. The another important, the last point that I will discuss today is the polarity and symmetry. So any polar molecule that will have a permanent dipole moment, right? Now the symmetry operations, particularly certain symmetry operations, can actually interchange the bonds and thereby cancel any possible net dipole moment. Okay, so in this case, only the molecules of point group C1, Cs and Cn and also CNV, they can be polar. But anything, if you have like D4H point group, it will not be a polar. You can easily find out that okay, there cannot be any net dipole moment. Okay, so like ammonia is polar, but benzene is non-polar. Okay, so with that I will leave you today. We will see again next week with a lot of new things regarding symmetry and their classification and etc. So till then, have a nice time. Thank you very much.